Hello, my name is Greg Kramer. Thank you for tuning in to my podcast. In the 21st century, technology is now a larger and more pervasive part of human life than ever has been before. Knowing this, it may be surprising and disappointing that funding for the science that creates this technology has gone down. Within the last decade or so, government funding for scientific research has fallen far below what it used to be. For the first time since the World War II era, the United States federal government funds less than 50% of the basic research carried out in the country. This is a far cry from the glory days of the Apollo program in the 60s and 70s, during which government funding for research peaked at 70% of the total. So, why has government funding for scientific research gone down in recent years? The answer lies in the public perception of science. Many in the general public don't understand the point of investigating deep scientific questions and would rather fund other endeavors. This in turn influences policymakers, whose job it is to decide how to allocate government funding. If they do not see any practical use for scientific research, they will not want to spend money on it. Why, after all, spend billions on telescopes and particle accelerators when you can use the money to solve world hunger or any other myriad of problems afflicting humanity? This perception, while certainly understandable, is rooted in misconception. Basic research is sometimes done without any specific practical purpose in mind, but this does not mean that the knowledge gained through such research will never be useful. There is a long history of scientists investigating problems out of sheer curiosity, and only later do they or someone else find a significant practical use for what they had learned. For this reason and others, the government should care about and fund expensive, large-scale science objectives. We know that scientific knowledge often leads to important inventions and innovations in the future. Much of humanity's technological progress has come from scientists who just wanted to understand how the world works. A good example to help illustrate this is the Global Positioning System, or GPS. GPS is a satellite-based navigation system originally designed for the U.S. military, which was later expanded to civilian use. If you ever use a navigation system in your car or travel on a plane, then GPS has ensured that you arrived safe and sound at your destination. A GPS receiver can determine your absolute position on the surface of the Earth to an accuracy of 5 to 10 meters in only a few seconds. In order to achieve results this precise, the clock hits from the atomic clock on the GPS satellites must be known to an accuracy of 20 to 30 nanoseconds. Since the satellites are in constant motion relative to the people of Earth, the effects from Albert Einstein's theory of relativity must be taken into account. The theory of relativity has two components, special and general relativity. Put simply, special relativity explains that space and time are not two separate things, they are interconnected. General relativity explains that mass curves space-time, what we experience as gravity, and this curvature changes the path objects follow. A GPS receiver can determine your absolute position on the surface of the Earth to an accuracy of 5 to 10 meters in only a few seconds. In order to achieve results this precise, the clock hits from the atomic clock on the GPS satellites must be known to an accuracy of 20 to 30 nanoseconds. Since the satellites are in constant motion relative to the people of Earth, the effects from Albert Einstein's theory of relativity must be taken into account. The theory of relativity has two components, special and general relativity. Put simply, special relativity explains that space and time are not two separate things, they are interconnected. General relativity explains that mass curves space-time, what we experience as gravity, and this curvature changes the path objects follow. This is essentially how orbits work, which comes into play with GPS satellites. The net result of these relativistic effects means that the clocks on each satellite should tick faster than clocks on the surface by about 38,000 nanoseconds. This is much greater than the 20 to 30 nanosecond precision required. If these effects were not taken into account, navigational info from GPS satellites would be false after only 2 minutes. Position errors would grow and the whole system would become completely useless almost instantly. This clearly shows that relativity is not just some abstract mathematical theory. It is vital to having a functional global navigation system. When Einstein was figuring out relativity, he had no way of knowing that his theory would be necessary in global navigation 100 years later. He simply wanted to understand the universe, and his unimpeded curiosity led to techniques that make all of our lives easier and safer. So even though basic scientific research might not produce practical results in the short term, it is often true that in the future, the knowledge we learned will be applicable to some technological innovation. Of course, not every shred of knowledge collected will lead to the next breakthrough. So, for argument's sake, consider a large, expensive scientific experiment. Let's say we gain a lot of new data from this experiment, but it is in a theoretical field. It is not likely that important new technology will be developed from what we learned. With this hypothetical scenario in mind, one might wonder if all of that was just pointless. Learning is great and all, but surely we could have made some real change in the world, done some real good instead. This should pose what I view to be a very important question. Is knowledge, not as a means to an end, but for its own sake, valuable? We live in a universe that is 13.8 billion years old. Some 5 billion years ago, a cloud of gas and dust collapsed under its own gravity, and the resultant extreme temperatures fused together atoms, creating a star. The leftover material coalesced into smaller bodies, planets, that orbited around the star. On the third planet, from some process still unknown, some wonderful accident of chemistry, the first life was born. Pressures from the surrounding environment forced the life to adapt, to better cope, slowly evolve into more complex forms to gain the best advantage. After billions of years, after countless stories of life and death, a new species arose, one with the intelligence and curiosity to figure most of this out. Even if knowing all of this doesn't give me food or money, I still think it matters. And I'm not the only one. From the beginning, humanity has asked questions about the nature of our existence. Even with the new comforts and stresses of modern life, our curiosity has remained strong. Scientific experiments and space exploration offer unique perspectives on the meaning and purpose questions we asked. It inspires people to think big, to think beyond just the Earth and beyond what we know. Moments of scientific triumph, like Neil Armstrong's famous first step on the moon, changed our culture forever. It pushed the limits of what we can do and what we can know. As we have seen, scientific research leads to numerous benefits for society. What we learn from doing research will often come back to help us develop new technologies. Many times, these innovations are things we would not have developed without doing the research first. Furthermore, answering questions about the nature of our universe satisfies a curiosity and fills us with a sense of wonder. Even for its own sake, knowledge matters, and it is research which generates new knowledge. Given all the benefits, it is clear that the government should care about and fund basic scientific research. Thank you everyone for watching. I hope you enjoyed.